Our next unit is going to focus on acids and bases. In order to understand what an acid and what a base is, we're going to go through one example of each. Hydrochloric acid, just simple HCl, and sodium hydroxide, NaOH. Now, in order to better understand what an acid really is when we talk about chemical reactions having to do with acids and bases, let's remember what our other two types of chemical reactions are. First, we've got precipitation. In a precipitation reaction, we had things like silver nitrate and sodium chloride coming together, both of them dissolving readily in water. But then when the silver and the chloride ions reached each other, they were not soluble and they would drop out of the solution as a solid AgCl. That's how we had that kind of chemical reaction. The other type was a redox reaction. When we were looking at redox reactions, we were looking at the oxidation states, and we were really kind of trying to figure out when these two interact, who owns which electrons? When they break up, where do those electrons go? Redox chemistry is all about looking at where are electrons coming from and going to. It's all about trading electrons. Remember, we could break this up into Cu2 plus 2 electrons going into copper, and Al going into Al3 plus 3 electrons. We were trading electrons. Well, in acid and base chemistry, what we're really trading is a little hydrogen. Let's look at what that really means. So if I've got hydrochloric acid and I put that into some water, that hydrochloric acid is going to dissociate into two respective ions. I'm going to have Cl minus and H plus. What is that H plus? Let's think about that. If I have hydrogen, just that entry on the periodic table, if we look at hydrogen, how many protons does hydrogen normally have? Well, 1. That's what makes it hydrogen. How many neutrons does it normally have? Well, we take our atomic mass, subtract our atomic number, which gets 0. Hydrogen has 0 neutrons. How many electrons would it have? Well, if it was neutral, it would have 1 electron to balance out its 1 proton. But it's not neutral here. This hydrogen right here has a positive charge, which means it's missing 1 electron. So it would normally have 1, but now it has 0. So this hydrogen here is really just a proton. That's it. So when we look at acid and base chemistry, this is really what we're throwing around. Where redox reactions, we're trading electrons, acid-base reactions are really all about trading those protons. So this is how we're going to define acids and bases. So when we have an acid, it's a substance that is going to donate a proton. When we have a base, it is a substance that is going to receive a proton. So if we look back at this initial example, HCl and NaOH, this is a base because that OH anion, that would love to accept a proton and become water. So this is the backbone of all acid-base reactions, is we're going to have hydrogen as an ion acting just as a proton, just a single proton moving around, bouncing between substances. So what makes these acids and bases so dangerous? What makes them so reactive? For that, we need to think back to our atomic model. Remember, when we have a normal atom like chlorine, let's just say chlorine right here, it's going to have this electron cloud around it. And this layered electron cloud is a certain distance from that nucleus. Now, if you remember all the way back when we first talked about this, that distance is very large in comparison to how big the protons and neutrons are. In fact, we said if we had an object about yay big, and we placed it on the middle of a football field, then called this the nucleus, that this would be the size of the nucleus of an atom, then the closest electron to it would be at the outer edge of the stadium. So this chlorine right here, the protons and neutrons that make up its nucleus are so extremely tiny and have such a vast distance to the nearest electron that this is going to be a huge radius in comparison. Now, when I have just a little H plus, a hydrogen cation, just a single proton, it doesn't have these layers of electrons keeping it from reacting with anything else. So when I say that I've just got a single proton here, what I really mean is it's like in Star Wars. I have these giant Star Destroyers, these giant, huge Star Destroyers that just look like giant triangles, trying to do battle with each other. And they're firing lasers back and forth, yada, yada, yada. And having a proton moving around in here is like having a tiny little X-Wing that is so tiny, it's just a little speck, that it doesn't even show up on the radar of either ship. That's what it's like having this proton in comparison to the size of these other molecules that it's going to be interacting with. On top of that, because it's just a single positive charge, it is going to be so extremely reactive that it's just going to attach to anything that comes near it. So that would be like, in this analogy, this little X-Wing that can't be detected, it's so much tinier, also has a gun that just shoots atom bombs everywhere. So it gets close enough to this Star Destroyer, just shoots an atom bomb at it, gone. Gets close enough to this one, shoots an atom bomb, gone. So when we're talking about a proton donator, this is actually a pretty significant deal. These protons are going to severely impact how these different molecules are able to interact. So if we have a varied concentration of our acids and bases, of our hydrogen cations, it is going to drastically change how other reactions proceed.